let me offer you an analogy. So what I have been saying is that for this rotor and these two planes where we are doing balancing, this is X, Y, that's Z, there is another plane which is the B plane, this is the A plane. What I said was I can put one mass here, measure the change in the vibration. So first I have to put a tracer on this one, so I get some signal. That's my time reference. So this distance is 2 pi. Then without this mass, just the rotor as is has some vibration signal, for which this is one period, so that's 2 pi, that's the average. That we'll call that A, and we'll call this distance psi A. In that case, the vibration is A bar cosine omega t minus psi A. All right. Then I add this trial mass, which MA, some magnitude, I'm saying X because it is in that direction. It is lined up perfectly with my reflector patch or whatever it is giving me my time trace, my time signal. Sorry, it's giving me the 0 reference point. Then let's say the vibration becomes whatever it was, plus delta A cos omega t minus, I need something else. I've forgotten what it was, but let me say psi A prime. Okay, I deleted the old drawing sheet and I've lost it, but over here this is the change. Now my point is that if, because of the symmetry, if I had instead not put the mass here but I had put it here, okay, MBX MAY equals MAX in magnitude or in size, but location is different. Location is the Y direction over here. In that case, what I would have is plus pi by 2, same magnitude. Okay. In this way, what I had described before as MAX, MAY, MBX, MBY, determining a state of vibration, which is, what I think I had called A1, A2, B1, B2, and then I want to make this 0. According to the Newton-Raphson strategy, I change this one and no change here, here and here. Then I change this one and no change here, here and here, and so on. But these two experiments need not be conducted. You may think that this is somehow cheating. It is not. It is because we are using an additional idea of the symmetry. And then if you like, I can offer you an analogy. So this is analogy. This is something that will help you think about it. This is not balancing at all. Okay, so let's say I have some plate and some part of the plate is fixed, and I have a point which I will call P and I have another point which I will call Q. My intention is to apply a force Fp over here and another force Fq over here, so that I obtain a displacement delta P here and I obtain a displacement delta Q over here. Okay, now I'm going to do this using some calculation. So what I will do is I will first apply a unit force here, and I will get unit force here. When I apply a unit force here, I'll get a displacement here which I will call delta P1, and I will get a displacement here which I will call delta Q1. Okay. In a separate experiment, I will put a unit force here, and then I will get a displacement here which is delta Q2, and I will get a displacement here which is delta P2, right? And then you see I will get delta, my final result is going to be delta P is equal to the force here, so that's Fp times delta P1, which is a measured quantity, plus the force here which is Fq times the force here, displacement here, which is delta P2. Okay, so this is one equation, and I will also have another equation which is delta Q is equal to Fp times delta Q1, because due to this Fp I will have this displacement delta Q1 plus Fq times delta Q2. Now this is known, you see, so this is specified here, this is specified, this part is measured, and I have two unknowns here, 1 and 2, and I have two equations. Okay, so I hope you see that there is a similarity with what we were doing with the balancing. Okay, now only it is in two, with two variables, that is all. But now suppose my structure was a perfect circle. Okay, suppose my structure was a perfect circle, then I'll be able to use symmetry, right? So let us say the point P here and the point Q is here. Okay, now when I apply a unit force at this location, I get a delta P1 and I get a delta Q1, which is due to a unit force here. Then when I apply a unit force here, by symmetry, you see, because it is perfectly round, over here what I was getting as delta P2, I don't need to measure it because it will be equal to delta Q1. This is the same process, but over here by applying one force here and measuring two displacements, I will get enough information for this system. Okay. Another way to look at it is if you have a 2 by 2 symmetric matrix, then you have this number here, this number is some other number, these are the same. So a 2 by 2 symmetric matrix actually has only 3 independent elements, but additionally over here we have some condition like this one is also equal to this one. There are only two numbers. Okay, so that is the end of this analogy. If you don't understand it but you understand the rest of the calculation, that is fine. Okay, with this idea that back to balancing. Okay, with this idea that there is this rotated effect, we can finally just look very briefly at single plane balancing. So let us say I have a rotor and one plane, and I'm going to do the balancing here, and here is that reflector and I'm getting some signal, you know, and so this is 2 pi, and I am also measuring the vibration signal here, somewhere, maybe here also. I have an accelerometer. And also this reflector. Okay, the accelerometer could be anywhere else also, it doesn't matter. So then I get, let us say, some that didn't work, but imagine that it was like this, then it would work. Okay, it's periodic, it's 2 pi periodic. Okay, so over here I am getting a vibration which is a cos omega t minus psi a. Okay, so let me, this in two-plane balancing, it is quite convenient to show it in a phasor diagram. So this is like a radius and this is like an angular position with a negative. So I will draw it here. Let us say it is like this. This angle is minus psi a. This distance is a. Okay, so this is this state of vibration without a trial mass is represented like this. Now I add a trial mass. When I add a trial mass over here, which I will draw in red for you to see, this is the trial mass. With the trial mass, the vibration state changes. Let us say the vibration state is now this. This is the vibration state, and this is the change in vibration state. I am showing it with phasors because every time I measure a vibration, I have an amplitude and I have a phase. What is the phase with respect to? With the spike, which is the same every time because it is the same reflector going round and round, some signal like that. Okay, so now you see I want it to rotate. Let us say this angle is 46 degrees. Okay, so now imagine, so I want it to rotate like this 46 degrees. That means I want it to have plus 46 degrees over here, right? Otherwise that is what will rotate it. And how will I do that? I just want it to arrive 46 degrees earlier, so I will go 46 degrees, and I know that this mass has to be removed from here and put here. Now also there is a magnitude. This has a magnitude and that may not be the same magnitude. Maybe this is, let this length be L1, let this length be L2. If L1 is equal to 1.3 L2, then I have to come here and times 1.3, and then I will get single plane balancing. This will go to 0. Okay, so the phasor diagram or geometrical method works well for single plane. Okay, good. Now what we have done is we have looked at rigid rotors so far. Two plane, assuming static balance. I don't want to mess with those equations here, that is all. And then experimental approach. We have not actually done it in a laboratory, but that's what we have done here, experimental approach. And then with 4 trial masses and then with 2 trial masses. And then we have done one plane or single plane, and we have used single trial mass. Okay, so with that I will stop balancing of rotors and I will move to balancing of a slider crank mechanism, which, as you may imagine, is relevant to balancing of engines. This is different. Okay, so it's quite a different topic, but it falls within the same type of theme of forces and movements in machines. So this is a single cylinder engine, right? So there is the crank, there is the connecting rod, there is the slider, and in this we will assume that the crank rotates at a constant speed. Okay, so the slider oscillates. Now this length is R, this length is L, R by L is less than 1. It's significantly less than 1. As you may imagine, when this comes to this side, if L is close to R, then the slider will hit this hinge point, right? So it will get really very close. For engines, we don't want that. For example, this will usually clear the bottom of the cylinder, right? And then the piston should not come out of the cylinder. So, for such reasons, this will be quite a bit less than 1, maybe 0.5 or even less, who knows. Okay, so you can look at some engines. Now, when we are trying to do this balancing, there are two things here. One is if this angle is theta, theta goes round and round, this angle is phi, phi remains between minus pi by 2 and pi by 2. Okay, so this is one thing that happens, although theta goes round and round. Okay, now what is the x direction position of this slider from here? That direction we can find using two simple equations. One is, see, remember, this is R, this is L. So I have R sine theta is equal to L sine phi. So sine phi is equal to lambda sine theta, where lambda is equal to R by L. Okay, so that's one thing. Now this distance x is equal to R cos theta plus L cos phi, which we can write as R cos theta plus L square root of 1 minus lambda square sine square theta. Okay, now why is it plus? Because this cos phi doesn't change sign, so there is no problem. Additionally, it should be clear that this part here becomes x is equal to R cos theta, we will say approximately, plus L 1 minus lambda square by 2 sine square theta plus dot dot dot. Because this is order lambda to the power 4, I am expanding this using this binomial theorem, or how Taylor series or whatever, for small lambda. Okay, now the sine squared theta also is basically, what is sine squared theta? The way I like to remember it is, so this is pi and that's 1. So sine square theta is equal to half minus half cos 2 theta. Okay, so the half part and this one just becomes a constant, and what we have is, x is some constant which we don't care about, plus r cos theta minus, let's see, plus, because this was a minus, so that's a plus, lambda square by 4 cos 2 theta. Okay, so now here is the point. If theta is equal to omega t, then x double dot is equal to, from here, 0, right, minus omega r sine, omega square r cos omega t minus, and there's going to be a 4 omega square coming from there, so lambda square, there's something wrong here, that is supposed to be multiplied by L. Okay, so so now this is equal to L, the 4 will cancel here, L lambda square omega square cos 2 omega t. The main point being, this is small and it is the second harmonic. There are ways to balance that, but we will focus only on this part. Okay, what does this mean? This means that to a reasonable approximation, the motion of this one is simply the horizontal motion of horizontal part of the motion of this one. Okay, to a reasonable approximation. Let us work with that. Okay, now here is this link which rotates about this point. If its center of mass is not coinciding with this point, then there is an unbalanced force. This is the static unbalance. We have just done single plane balancing, so you know that that will cause some forces to act on the frame, right? So you suppose our engine is like this and it is on some bigger thing, like maybe a motorcycle, right? So the engine is here. So if there is an eccentric mass going round and round, there is a force from the frame that is needed to give it that acceleration, and the reaction on the frame is the opposite, and the frame reacts to that. Okay, now you may say that, well, I assume the frame is not moving. The motion of the frame is much smaller than the motion of that mass, and so that's a reasonable approximation. You want to do it more carefully, you can. Nothing really changes. Okay, all right, so now we have this which has possibly some unbalance. Then we have this connecting rod, and the connecting rod is not really, two-point masses, but I am showing it like that for reasons that will become very clear soon. Okay, all right. Now, why am I thinking of the connecting rod as 2-point masses? This is the slider. Let me call this MA and MB as the point masses that I am saying I will use for the connecting rod, and this is the crank part. The reason I want to do this for the connecting rod is to simplify my force and moment calculation. So let me show you that here. Okay, so the connecting rod actually maybe looks like this. It has a hinge here, it has a hinge here. It's usually symmetric, so its center of mass is some point G on that line. This point is A, this point is B. I want MA to be dynamically equivalent, MA and MB with the massless rigid rod to be dynamically equivalent. This requires 3 equations in 2 unknowns to be true. For example, if this is the mass of the connecting rod, then I have MA plus MB minus MC should be 0. That's one equation. Total mass has to be the same. Center of mass location must be the same. That means MA times AG minus MB times BG should be equal to 0. AG and BG are distances. Okay, so that means the center of mass is located in the same place. Suppose this has a moment of inertia about the center of mass, JC, C for connecting rod. Then we require MA times AG square plus MB times BG square minus JC should be 0. Clearly you can see that these are 3 equations and 2 unknowns. We can't in general have an exact solution. What should we do? Well, some of you may think of a least squares solution, and if we think of a least squares solution, one way to do it is to take this one and square it, and take this one and square it, and take this one and square it, and add them up and minimize with respect to MA and MB. There is a problem. We don't want to do that because this has units of mass, this has units of mass times length, this has units of mass times length square. So we should have same units, otherwise what are we even adding? To think of what we can normalize this, so this actually we should divide by some L0 square, right, where L0 is some meaningful length for this problem, and this we should divide by some L0 to the power 4. If you look at this, let us say this is the engine, this is the rotating part, this is the connecting rod, and this is, you know, some motorcycle or some vehicle, some car. Then a typical length scale in this car is something like this, you see, and A, G and BG are much smaller than L0. Okay, so if we are interested in the response of the car, maybe rotary vibration, vibrations of the frame, things like that, then I just made a mistake. Then we should normalize with respect to this L0. But when we do, what happens is that this one gets extremely small weight. So we might as well throw it away. These are the equations that remain, and therefore we basically match these 2 conditions: total mass and center of mass location. Okay, once we match this, we get a very good approximation to the behavior, and we proceed. Okay, so now we are here. This is our crank, this is the connecting rod, this is the slider. But what happened is this point mass can be assigned to the slider. So M slider plus MB. This is massless. Now over here I have MA, and over here, somewhere over here, I have M of the crank, right? And what I do is I can add an M balance over here so that the center of mass of this combined crank including MA coincides with this one. Then there are no unbalanced forces provided this omega is a constant. When that happens, I still have the acceleration of this one, which is required to be achieved, and for that there are forces from the frame. All right. So, and as we have discussed, to a reasonable approximation, that is just the horizontal part of the acceleration of this point, right? Because it is the position of this has the same variation as the horizontal component of this. Okay. Alright, so this will cause vibrations in the engine frame. In fact, if you look, you will find there is actually a motorcycle design where they have pistons like this, connecting rod. Somehow they arrange it in such a way, I don't know how it is done over here, but this piston, this one goes up and down, this one goes up and down, and the piston part is exactly cancelled. So those motorcycles are smooth. There may be other technological reasons for not using it, but I have seen motorcycles like that. There are also other things that you may be interested in. For example, your engine may be sitting on some structure which for some reason is more susceptible to unbalanced forces in this direction and sort of relatively more rigid to unbalanced forces in this direction. In that case, what you can do is the horizontal component of this one can be cancelled by a precisely equal and opposite extra mass over here. So the horizontal component will cancel, but the vertical component will not be. Let me say that again. I'm sorry, that's not what I wanted. What I meant to say is, if I leave some unbalanced mass over here or over here or wherever it is, you see, if I leave a negative unbalanced mass here, that is exactly the same as putting a positive unbalanced mass here. Let me have a negative unbalanced mass here. That negative unbalanced mass has this acceleration which matches this acceleration. That negative mass can be made equal to this one, and then what will happen is actually just this vertical part will be there. Okay, because the horizontal part will be cancelled. In this way, this unbalanced force can be changed to this unbalanced force, or a rotating unbalanced force, or some elliptical, sort of effectively elliptical force, okay, at some angle. And people, for example, single cylinder motorcycle engines, right, they pay attention to these things. There are even fancier things that you can do, and I will just mention it, and that is, you can have a counter rotating. So if this one is rotating like this, you can have another counter rotating shaft which is, you know, close by and which rotates at nearly the same speed, and I'm sorry, at exactly the same speed. And then what happens is, you see, if I have one mass that goes like this and another mass that goes like this, then the vertical accelerations of these two will be cancelled, and all that will be there is a horizontal unbalanced force, and that horizontal unbalanced force can be chosen to balance this one. But what such a thing does is, you can't obviously put the rotors exactly in the same place. They're a bit nearby by the same arguments as we were saying earlier. The net forces are to be balanced, but what happens is it adds more parts. You need gearing, you need extra rotors and so on. I had a student who worked for TVS Motor Company. He told me that he has seen motorcycles that do that, but it is not there in their model. Okay, so this is balancing of the slider crank mechanism. I have not worked out the equations in this lecture, but you can work them out or look at the book. I will send you some assignments with references to specific pages in the book, and when you work them through, all of these matters will become clearer. Thank you.